Hello and welcome to the next lesson, which is forces in one dimension, and we're looking at it's a grade 11 review, so a 3U review. So what's your goal today? I want you to be able to explain Newton's three laws and be able to apply them for one dimension. All right, so let's head into this note. So a couple of definitions for you. They're already typed up. Force. Force is a push or pull in a given direction. So again, it will have magnitude. All right, magnitude, and it will have direction. Mass. Remember that mass is a scalar value. All right, so I'll put that at the end, where force is a vector value. So mass is the amount of matter in an object. So just how much material makes up that particular object. Weight is the counterpart, and these two words get interchanged. Very important when you're writing solutions on tests that you are able to differentiate between them, because that's what I'm really looking for when I'm marking in terms of the communication. So weight is the force due to gravity acting on an object. So again, it will have magnitude and it will have direction. So very important to differentiate between them. And force of gravity. Force of gravity. It is the force of mutual attraction. So that's from the grade 11 course. We talked about it briefly there. It's going to play a much larger role in Unit 3 in this course, but we do need to go through that. So it's that mutual attraction between any object and the Earth for this particular unit. So we're only talking about objects on Earth. So our formula again, gravitational constant, mass 1, mass 2, all over r squared. And remember our notation here, G is the gravitational constant. Which is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. It's that fudge number that makes everything work out well. Mass 1 and M2, okay, mass of both objects. And finally, your R value is your distance between objects. I'll put distance between centers of objects for the larger objects. So if we're talking about planets, gotta go right to the center. Okay, so that's pure straight review here. Let's talk about that formula that we have there, and we're going to talk about it in more detail a little bit later on. But if I'm to separate out for us in this one, the G, the first M, which is the mass of the Earth, I capitalize it, and I divide that by our R squared. Okay, what we end up with, and remember, in terms of units here, this is in newtons. All right, it's a force. And if I take the GM, divide that by R squared, and then multiply by mass 2, what happens is that first term is simply our accepted value of G on Earth, okay? Because it is the acceleration in meters per second, but it's also what we call our gravitational field strength. So it is simply in kilograms, or sorry, newtons per kilogram would be the units here. So let's put it in this format. So let's go with G, and in brackets I'll put newtons per kilogram. So it is your field strength multiplied by M2, which is measured in kilograms. And again, on Earth, that G, or newtons per kilogram, that's simply what we're ending up with is mass times acceleration. So G is an acceleration, right? It's our 9.81. So we end up with, and still in red here, it's our acceleration times our mass to simplify, which is just ma. So there's your connection with force due to gravity and mass times acceleration, or the FU-ma, Newton's first law. Okay, so what's important here? Okay, obviously this is going to be important. Okay, this bottom component here, Just want to show you what that connection is. It's going to be more important for us in Unit 3. We're actually going to go through it, and the expectation is you are able to go and understand and explain those steps. So just as a heads up. Okay, let's talk about free body diagrams for a second. So a simple diagram shows the forces acting on an object. So let's talk about two particular objects here. So we're going to go with object 1 and object 2. So the first object, flat surface, let's call it a box. Second one, what we'll have on every object that is on a planet, it's going to be influenced by some form of force due to gravity. And that's true for both objects. Now, if it's sitting on a surface, and for these two particular ones, I put them on a surface, they will experience a normal force because they will not be accelerating into the ground. The ground is supporting them, and that support force is that normal force. Now we have two particular scenarios here, okay? And it's that horizontal force. So if we call this one application force, and the one opposing it, it's really your force due to friction. Okay, remember, force due to friction opposes motion. All right, and I draw them out, relatively the same size, force due to friction. We end up with a scenario like this. Now, why did I draw two identical diagrams? Because what I need you to be able to understand or be able to differentiate between is this situation right here. Oops, if FR and FA are equal, so FR equals, I don't know where the R came from. Who said that? Come on now. Force due to friction, FF equals FA. How does that compare to if I tell you the applied force is greater than the force due to friction? How do they compare? So in this one we have all forces are balanced. All right, and if I asked about the motion, you're going to tell me, hopefully, that it is in a constant state of uniform motion. Which means two things. It could be stationary, or if it's not stationary, it's moving at a constant velocity. Moving at, I guess, a constant rate. And you can't tell that from the diagram, which it is. It's one of those two particular scenarios. You have to know more information to differentiate between the two. So if forces are balanced, it's in a state of uniform motion, so that means it could be stationary, or it could be you're in the car, you put cruise control on. So you're not accelerating, but you're not slowing down. Whereas in the other one, we have unbalanced forces. Unbalanced forces. And because FA is greater, we have acceleration to the right in this particular drawing. Acceleration to the right. Okay, so there we are. There's the difference between, and that's why the free body diagrams are very important, because they tell us a whole lot of information, or tell us that we don't have enough information. So I can't stress the importance of those free body diagrams. All right, so Newton's 3 laws. I'm going to go through and put them up with video magic here. I'm going to pause it, put the video up, and I'll tell you that you need to pause it if you want to record it. So here we go. And voila, there it is. So our 3 laws: an object remains in its current state of motion unless acted upon by an unbalanced force. Remember that a textbook sitting on a desk is happy to sit on that desk until someone pushes the book off. Or think of yourself on the weekend after a long day, sitting on the couch. It will require an immense amount of unbalanced force to remove you from the couch, as some of your parents will probably agree with. The second one, Fu equals ma. It's an unbalanced force caused by the product of mass and acceleration. So this is the Fu law from the grade 11 course. And finally, every action has an equal and opposite reaction. So for example, if you accidentally get drawn into a fight, you can argue with the principle that it wasn't my fist that was hitting the forehead, it was the face, it was the person's face that was continually pummeling my fist. Look at my fist and the poor shape it's in because of that person continually headbutting it. You never heard it here. Any claims otherwise, I will completely deny. I'm moving to the next slide, so if you need to keep writing, hit the pause button. Hurry, 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 too late. Okay, so a couple of examples. Again, this is from grade 11. A 0.24 kilogram ball accelerated at 5 meters per second squared north. What is the net force acting on the ball? So net force, okay. So need to use both terminology. So net force and unbalanced force mean the same thing. They can be used interchangeably. You can interchange them as you wish. So it's important to recognize I know that. So what do I know? I know my mass is 0.24 kilograms. I know acceleration, 5 meters per second squared to the north. So what is my force? Well, we know that Fu equals ma. So we are looking for Fu. 0.24 times acceleration is 5. So we're calculating that out. So 0.24 times 5. You think I'd pick easier numbers for my example, so I just do them in my head. Now remember, force and direction, or sorry, Fu and acceleration are always in the same direction. All right, that unbalanced force is caused by acceleration. So if acceleration's to the south, unbalanced force has to be the south. They're tied together, they're linked together. They're both vectors, and they're vectors that are causing whatever action to occur. So they have to conform. So therefore, net force is 1 point newtons, and yes, the direction is very, very important. And there we are. So I believe I have 2 more examples. So at this point, I'm going to cut this video off so I'm not rushed. Get the next video done. It should be fairly quick, and then you're off to the races. See you in the next video.